Using a solution freezing point to calculate a molar mass. So you're going to use the relationship between the difference between the boiling point of the pure solvent and the boiling point of the solution. That's your freezing point depression, that solution is going to have a lower freezing point than the pure solvent would have. You're going to need the molar freezing point constant, which is Kf, and m(f) is the molality. So the delta TF we're going to be able to calculate because we've been given the freezing point of the solution, and we're told the solvent is cyclohexane. So we are going to look up the freezing point of cyclohexane. So let's just put that down as a reminder. And we're going to need the molar freezing point depression constant of cyclohexane. So these are all constants that can be looked up. So you're going to need to use your ALEKS data tab. So excuse me, because the student view can be a little bit tricky to show. It looks different for me than it does for you. Oh, please don't do that. No, no, please don't make me do another knowledge check. I had this working a minute ago. Right, start my path. Okay. So obviously this is just, for illustrative purposes. So if we look over the right-hand side, you are looking for this little bar chart type thing that says data. If you click on that, please cooperate. It's taking a bajillion years. You want to look, if you scroll down, there's molar freezing point depression and boiling point elevation constants. So our solvent is cyclohexane. So we want the normal boiling point of cyclohexane, which is in degrees Celsius. So not boiling point, melting point, 6.7 degrees Celsius. So I'm going to put a little symbol here for that's the normal boiling point of the pure substance, and that was 6.7 degrees Celsius. And the molar freezing point depression constant for cyclohexane is 20.8. 20.8, and that's degrees Celsius per molality, and molality, as we know, is moles per kilogram, so that is written as kilogram per mole that way because it's degrees Celsius over molality. All right, so I can get rid of that now, probably, if I can click a button correctly. All right, so let's get back to our question. We've got the things we need, so we can rearrange and solve for our molality. So our molality is going to be our delta TF divided by our KF, and that is going to give me my molality, which is in moles per kilogram. And I have my kilograms of solvent, right? So I can then use that to work out how many moles of solute I have. So first things first, the delta T. Oh, I didn't work out the delta T. Well, the freezing point of the solution is 6.5, and the freezing point of the pure solvent is 6.7. So 6.7 minus 6.5 is going to give me a difference of 0.2 degrees Celsius, and divide that by 20.8 it was, wasn't it? I don't think I typed it out. Degrees Celsius per molarity. So our units, the degrees Celsius is going to cancel out, and 1 over molality is just going to give me units of molality, and that turns out to be 0.009615 molality. I'm just going to leave it like that for a second. So as we know, molality, if I could type molality, little m, is in moles per kilogram. So that is the amount of solute in moles divided by the mass. Okay, mass of solvent in kilograms. So if I have my molality, well, I do because I just calculated it, and I've got my mass of my solvent in kilograms, then I can calculate the amount of moles of my solute I have. So note the 70 grams of cyclohexane, that is our solvent. It is our unknown that is the solute, right? The thing we don't know. So this certain molecular compound, we don't know what it is, that is our solute. Just to make sure we know what's what. Okay, so we have the molality of our solution. We're going to rearrange and solve for our amount of moles of solute. However, we have to be careful because we've got our mass of our solvent in kilograms. So our moles of solute, if I could type, is going to be our molality. I will go ahead and write out the molality in degrees Celsius per molality. And remember, molality is moles per kilogram, so it's going to be over moles times kilogram. So you just put kilogram on top there. And then molality times the mass of solvent, so mass of solvent in kgs. So our kgs is going to cancel out, and we're going to end up with just our, didn't need that. Looking at the molar constant, aren't I? Molality is in kilograms per mole, mass of solvent is kilograms, and we're going to end up with our number of moles of solvent. That's talking and typing, that is. Okay, so now the only thing we have to worry about is that our mass of our solvent was given to us in grams, 70 grams. So I would just go ahead and make sure I do a unit conversion. So I can take that molality that I calculated, 0.009615, and write it out as moles per kilogram. So we can see that the kilograms are cancelling. My mass of solvent was given to me as grams, so 70.0 grams. I'm going to have to insert a unit conversion to get from grams to kilograms. 1 kilogram is 10 to the power of 3 grams. Okay, so let's just make sure we're being consistent with these units here. So we should end up with the kilograms and the grams cancelling out. So we just end up with the units of moles, which is good. So the number of moles of our solute that we should get is, typey, 0.06731. And I know we're only going to be giving this to one significant digit, so I'm not getting too worried. So molar mass, our units of molar mass is always given in grams per mole. So in order to calculate our molar mass of our solute, if we know the mass in grams of our solute and we know how many moles of solute we got, we can make that ratio, right? So we have 538 milligrams, and so I'm going to have to convert milligrams into grams. Again, we can do that just with dimensional analysis, right? Unit conversion. So the amount of moles we calculated was 6731. So at the moment, my units would be milligrams per mole. So I have to just convert milligrams to grams. We know that 1 milligram is 10 to the minus 3 grams. So hopefully we can see from dimensional analysis that we have sorted that out, and we should get final units of grams per mole, which is the units that molar mass is in, and we get like 799.288 blah blah blah, whatever it is, grams per mole. So we're asked to do that to 1 sig fig, so that's obviously going to round to like 800, blah blah blah. So to 1 sig fig, that's going to be 8 times 10 to the power of 2 grams per mole. Done and done.